Okay, example 12 is actually two different examples, but they're both interesting, so let's go through them. The first is Fermat numbers, and this is a good example because it forces us to separate what is the function, what is the predicate, and then our full predicate statement. Fermat numbers are written out f of sub n equals 2 to the 2 to the n plus 1, right? F of 0 is 2 to the 2 to the 0 plus 1. 2 to the 0, anything to the 0 is 1. 2 to the 1 is itself 2. 2 plus 1 is 3, right? F of 1 equals 2 to the 2 to the 1 plus 1. Any number raised to the 1 power is itself. So 2 squared is 4 plus 1 is 5. F to the 2 is going to be 2 to the 2 to the 2 plus 1. 2 raised to the 2 is 4. 2 raised to the 4th power is 16 plus 1 is 17. Notice so far they're all prime. And I'm not going to keep doing all of these, but f to the 3 is 257, and f to the 4 is 65,537. So those are Fermat numbers. And the predicate, Fermat's theorem, all Fermat numbers are prime numbers. Right? The result of all of those will exist in the prime space. This is false. And we know this is false because F5 is 4 billion something. And that number is not a prime number. That is decomposable. And we know actually that F5 through F20 are decomposable. At the time that Fermat came up with this predicate, a number like that would be really, really hard to test if that was decomposable, if you could break it apart into factors. Nowadays with a computer that takes 2 seconds, but back then it was a really big challenge. So that is why he came up with that theorem. But what if we had a slightly weaker statement? Instead of saying all Fermat numbers are prime, what if we said there's an infinite number of Fermat numbers that are prime? That's actually a very different predicate. Let's look at that. Okay, so Fermat's statement was for all n, f of n is prime. Or we could just say for all n, s of n is true, right? That's Fermat's statement. If we want to say there are infinite number of Fermat numbers that are prime, we would say for all m in the entire set of natural numbers. I don't know why that natural number n is so hard for me to do. You know this is a natural number n. For all m that are in the set of natural numbers, there exists some n greater than m such that s of n is true. That statement says that there are an infinite number of Fermat numbers that are prime. What would be the opposite, the negation of that statement? The negation would be there exists some m in this set of natural numbers such that all n greater than m, s of n is not true, right? So that's saying that there are not infinitely many, that there's a finite number, that if you picked a large enough m, there would be no Fermat primes higher than that. Which is true? We don't actually know. Neither have been proven yet, and that's okay. The point of this example is just to understand how we take these statements and put them into predicate logic. And once they're in predicate logic, then we can work on proving or disproving them, which isn't part of this class, but putting them into predicate logic is. All right, the second half of this example involves some basic high school geometry, which isn't necessary, but I'm going to explain it because it's kind of fun. Essentially, you can draw any shape with equal length sides using nothing but a straight edge and a compass. So let's kind of make a few marks here. We'll mark a point there, and we'll mark a point there, and we'll call these points A and B. All right, right. So if the compass goes through B, we can kind of draw around it there. And then what we're really interested in are going to be these parts up here. Because when we move the compass over to B, those are the intersection points. What we've done is we've created a line that is perpendicular to the AB line. And we're going to go ahead and call these C and D. Now, the important thing is, and then we're going to, let me create a ruler, and then over here, where that ruler crosses the circle from centered on A, is going to be point, it's blue, but you get the idea. That's going to be point E. Between C, D, and E, we have an equilateral triangle. And let me bring back that ruler. So let's put this over on E and bring this down to D. Bring that up here to point C. Finally bring that down there. So we're able to draw an equilateral triangle using nothing but a straight edge and a compass. This same technique will also work for a square or a pentagon or for a whole bunch of equal-sided polygons. That brings us to the question. All right, so if our method is P of n, if P of n equals a regular n-sided polygon can be constructed with a compass and straight edge. So that is our statement, right? That is our predicate, P of n. The question is, for which n is this true? Well, the Greeks proved that for all k that exists in the set of natural numbers, P of 3 times 2 to the k and P of 5 times 2 to the k, that's supposed to be a parentheses, the Greeks proved that to be true. So we know for any k in natural numbers, if it's 3 times 2 raised to that or 5 times 2 raised to that, that is a valid n. So this is sitting in for the n up here. So we know at least in those two cases, P of n is true. Then Pierre Wansel proved that really you can have the m times 2 to the k format as long as m is odd, right? M is a member of the odd set of numbers. So in all of those cases, you can construct an n-sided polygon, right? The key thing here is to understand how we go from this kind of real-world geometric problem into stating it using predicate logic. If you have any questions, ask in the forum below.